In this video tutorial, we will be calculating enthalpy of reaction using the bond energy method, Hess's Law method, and heats of formation method. So the first method we'll be looking at is called the bond energy method. It's not a super accurate method in comparison to the other two, but it does a pretty good job of giving you a rough estimate in terms of magnitude and also in terms of whether the reaction is exothermic or endothermic. With this method, you will have to first write out the chemical equation, don't forget to balance it, and then you may have to draw the Lewis diagrams for each compound inside. This will allow you to determine what type of bonds are going to be broken in order to create a new compound and which type of bonds will be formed at that point. So for this specific example, we will need to break up the hydrogen-hydrogen bond over here, H2, and the fluorine-fluorine bond over here. In the process, that will free you up to produce an HF bond instead, but not just one, because when you balance the equation, there's two hydrogen fluorides being produced. So you have to create two of these bonds. Using this equation, the change in energy is the energy used for breaking the bonds, subtract the energy formed in making the bonds. We can then substitute those values from our average bond energies chart. This chart will always be given to you on a test, so there's no need to memorize it. So, to break an HH bond, it requires 436 kilojoules per mole. So there that is. To break an FF bond, it requires 155 kilojoules per mole. That's where that number comes from. Add that all up, and that's the energy required to break all the bonds we need to break. Then we need to find out how much energy is required to form these bonds. So hydrogen fluoride is right over here, 567 kilojoules per mole. And since there's two of them, we multiply that by 2. Subtract these two values, and you get negative 543 kilojoules per mole for the enthalpy for this particular reaction. Unfortunately, this answer is a little ambiguous, especially when it comes to the units, because right now it says negative 543 kilojoules of energy is released per mole. But per mole of which one? Hydrogen, fluorine, or hydrofluoride. So a more correct way to express this answer would be to say negative 543 kilojoules of energy is the enthalpy for this particular reaction as written. But if you have to express the answer in kilojoules per mole, you should say the enthalpy for this reaction is negative 543 kilojoules per mole of hydrogen, since there's a 1 coefficient in front of here. Or you could say kilojoules per mole of fluorine, because it's a 1 as well. But because there's a 2 in front of this, you'd have to say 543 kilojoules per 2 moles of hydrogen fluoride. Alright, so we just have to be specific in order to avoid confusion. While we're on the topic of technicalities and avoiding confusion, try to avoid saying negative 543 kilojoules of energy is released per mole of hydrogen. Alright, it's not technically correct because you're saying negative 543 and then you're saying the word released as well. By definition, when you have a negative value, that means the system is releasing the energy. So it's already assumed or inferred that you are releasing energy. There's no need to say the word released again, otherwise it makes it sound like you're releasing a negative amount. So if you're releasing a negative amount, then that technically means that you're absorbing, which is not what you want at all. So a better way of saying it would be 543 kilojoules of energy is released. And by using the word released, the reader already knows that 543 must be a negative value. But if you want to avoid this confusion altogether, just don't use the word released or absorbed. Just say the enthalpy of the reaction is negative 543 kilojoules per mole of hydrogen gas, and the reader will infer that the negative value means it's being released. If it was a positive value, then that means it's absorbed. There's no need to say released or absorbed. It becomes just contradictory sometimes. Now, a common mistake that I find students will make is that they'll memorize this equation incorrectly. On a test, they might write down making bonds, subtract breaking bonds, when it should be the other way around. So if you are the type that makes silly mistakes like this, I would recommend that you get rid of the subtraction sign altogether and make it an addition sign. From there, you must remember that energy used for breaking bonds will always be a positive enthalpy value. So I must add energy, 436 kilojoules per mole to break the hydrogen, 155 kilojoules per mole to break the fluorine. Meanwhile, forming bonds is always going to be a negative value because energy will be released. And so this bond energy would then be a negative 567 kilojoules per mole, which you have to multiply by 2. Once you do this, it won't matter if you had switched these two variables by accident. So as an example, positive 3 plus a negative 2 gives you positive 1. But what if I switched it by accident on a test and I said, oh, is it making bonds plus breaking bonds? It doesn't make a difference because negative 2 plus a positive 3 is still positive 1. Alright, so again, my recommendation, just make an addition sign so you don't have to worry which side is which. Is it breaking minus formed or formed minus breaking? It really won't matter. But if you do decide to do this, make sure that you have to have the breaking bonds subtracting the making bonds. I think your textbook, version 1 of your textbook has screwed this one up. it actually says making minus breaking, which is incorrect. All right? Or just avoid the confusion altogether and replace the subtraction with an addition. Just make sure you know which enthalpies are positive, which ones are negative in order for this to work out. As I mentioned previously, when it comes to the bond energy method, it's important that you draw out the Lewis diagrams because it makes a difference if you have a CC single bond, CC double bond, or CC triple bond involved. All right? Because CC single bond is 348, while a double bond is 614, and a triple bond is 839. So unless you drew the Lewis diagram and realized there was a double bond present, you may accidentally think it's actually a single bond. It's also very helpful to draw these things out so you can actually count out how many of these CH bonds are present that need to be broken, how many of these CC bonds and CH bonds are necessary to be formed, etc., etc. It just makes it less likely for you to make a silly mistake, that's all. Unfortunately, the questions you get on a test will rarely be in this format. Instead, they'll be written as chemical formulas like this, and so you'll have to be able to draw the Lewis structures yourself. Now, the second method we use to calculate enthalpy change takes advantage of Hess's law, which states that the enthalpy change for a physical or chemical process depends only on the initial and final states of the system. It is independent of the reaction pathway taken. So if you look at these three reactions, they all start off with initial reactant A, and they all end up with final products B. Hess's law states that the enthalpy change for each of these three reactions is identical, regardless of how many intermediate steps were taken along the way to get there. Like climbing a mountain, it doesn't matter what path you took to get there, the long scenic route or the direct route, in the end, the height difference remains the same. Thus, Hess's law allows us to determine the change in enthalpy for reactions that may not be easily determined through experimentation. So let's say I wanted to find the enthalpy change from initial reactants A to final products B. Unfortunately, the direct reaction is either too expensive, too dangerous, or maybe I don't have the equipment for it. Well, Hess's law allows me to take an alternate route, one that may require multiple steps, but perhaps it's cheaper to go this route, or maybe it's less dangerous, or maybe I do have the equipment to do this, but it just takes more steps, that's all. In the end, though, I will still get the same answer as if I had just gone directly from A to B. Alright, so now that we have Hess's law, we can use it to help us manipulate equations in order to calculate enthalpy values that we otherwise normally could not have. Alright, so chemical equations may be manipulated in the following ways. Method number 1, multiplying an equation by a constant also multiplies its enthalpy value. So in this reaction over here, A plus 3B produces C and also 100 kilojoules of energy. Since the energy is written on the product side, this is an exothermic reaction. Now if I double the amount of reactants and products involved in this chemical reaction, it makes sense that I should also double the amount of energy produced, which is what we see here. A plus 3B produces C and 100 kilojoules of energy. Well, double that. 2A plus 6B would produce 2C, but also 200 kilojoules of energy. If an equation is reversed, then its enthalpy must change its sign as well. So when this reaction moves forward to the right, it's releasing 100 kilojoules of energy. So this is going to be an exothermic reaction. So if going forward is exothermic, then going in reverse must be endothermic. It absorbs energy. Alright, so we have negative 100 kilojoules being lost by the reaction in this direction. But if we go in the reverse direction, it's going to be absorbing energy instead. So positive 100 kilojoules. When adding equations, the product of one step can cancel out the reactant of another if they are the same. And then, of course, in those cases, enthalpy values can also be added. So for instance, A is a reactant, but A is also a product. So that means A didn't really participate in the reaction. It started off as A, it ended off as A, nothing really happened to it. So I can cancel them out. You'll notice that 3B is a reactant on this reaction, but it's also a reactant in this reaction. So altogether I needed 6 B's for this reaction to occur. 1 fluorine is required, but in the process you create a C here, but you also produce a C over here, so altogether you produce 2 C's. And then at that point we can just add up the enthalpy values to get a net enthalpy change of negative 140 kilojoules. Alright, so you can cancel out compounds that appear on both sides, and you can consolidate and add up compounds that appear on the same side. Alright, so let's try this out. Let's pretend this reaction is too difficult to measure the enthalpy change for, and so what we're going to do is we're going to use a bunch of other chemical reactions in order to help us assemble this target equation. Alright, so determine the enthalpy change for the reaction below using the heats of formation equations provided on the back of this handout. So these are standard molar enthalpies of formation. They will be given to you on a test. You don't have to memorize all this, but you do need to know how to use this and which equations to use. Now they're called molar enthalpies of formation because they describe the energy change when you're trying to form 1 mole of this particular substance from elements in their pure natural state. So in this case, if you wanted to form 1 mole of Ag2O from its elemental building blocks, it would require 30.66 kilojoules of energy to be released. So this would be an exothermic reaction. Now you'll notice you're allowed to have coefficients that are fractions. This is because by convention, the coefficient in front of the compound you're trying to form, the compound you're trying to make, should always be a 1. So it's always measured in kilojoules per 1 mole of this guy over here. Otherwise, if you wanted whole numbers, you would then have to multiply everything by 2 to get a whole number. So multiply this one to get 4. Now that this half is turned into a 1 whole coefficient. This is a 2, but then you got to double this one. Now if you said kilojoules per mole, it'd be per mole of the oxygen. Alright, so by convention we would like to say kilojoules per mole of the compound being formed. So in order to do that, I got to divide everything by 2. But that would end up with a fraction over here. But this is still preferable to have this one measured in kilojoules per mole of the compound being formed and just having to live with this fraction of a coefficient. That's okay. Alright, so back to this equation. I want to essentially assemble this using these over here. So let's take a look and see what kind of building blocks I need. I need a C3H8, and here I found an equation that produces C3H8. I then need carbon dioxide gas, and I can find that one over here. Finally, I need H2O liquid, which is present over here. Please keep in mind that H2O gas versus H2O solid have different enthalpy values, so make sure you pay attention to which state of matter we're talking about. In this case, it's a liquid. Now, you'll notice that I've skipped the oxygen. That's because oxygen is an element in its pure natural state, and we kind of use them as a baseline, a starting point. So elements in their pure natural state are always given an enthalpy value of 0. So we don't really have to worry about them. But as you'll see in a few moments, many of the equations that we're using to build our target equation already include oxygen. So there's no need to find a separate equation just for the oxygen. Anyway, I'm going to use these 3 equations that I obtained from the enthalpies of formation chart, and I'm going to manipulate them and use Hess's law to combine them into this target equation. Now, a little hint, you'll notice that I've labeled them as equations A, B, and C. I do not recommend that you label them as equations 1, 2, and 3. I've seen this mistake being made on tests where students will write them as equation 1, equation 2, equation 3, label them that way, and of course they make the mistake thinking, oh, there's a 13 for a coefficient, a 2 for a coefficient, and a 3 as a coefficient. So just be careful of that. Whoops. Alright, so here I have C3H8 on the product side when it's supposed to be on the reactant side. So what I'm going to do is I'm going to reverse this first equation. In so doing, my C3H8 is on the proper side, the reactant side. But don't forget, if you reverse the equation, this exothermic reaction is now endothermic. So it was negative 104.16, now it's positive 104.16. Looking at equation B, I see water is on the product side. Well, that's where it's supposed to be, so that's fine. Don't need to reverse this. But you'll notice that the target equation has 4 waters involved. So I'm going to multiply the water, equation B, by 4 as well. In so doing, I've also multiplied the enthalpy change by 4. Same thing with the carbon dioxide. It's on the right-hand side, the product side, so that's okay. But the target equation has 3 carbon dioxides, while this currently only has 1. So I'm going to multiply this equation, C, by 3. But don't forget, you also have to multiply the enthalpy value by 3 as well. I can now add up and consolidate the overall equation, canceling out compounds that appear on both sides of the equation, and also consolidating those that appear on the same side. So the 2 and the 3 oxygens turn into 5 oxygens. And look at that. My equation at the bottom now looks like the equation at the top. And by adding up these enthalpy values using Hess's law, I have found the overall enthalpy change for this entire reaction is negative 2214.38 kilojoules. Now, if the question asks for it to be expressed in kilojoules per mole, you have to be specific. So I can say it's negative 2214.38 kilojoules per 1 mole of C3H8, or kilojoules per 5 moles of oxygen, or kilojoules per 4 moles of water, or kilojoules per 3 moles of CO2. So if I wanted it in kilojoules per just 1 mole of CO2, I'd have to divide this by 3. If I wanted this in kilojoules per 1 mole of water, divide this number by 4. If I wanted it in kilojoules per 1 mole of oxygen, divide it by the coefficient of 5. Alright, so here we've used Hess's law, taking the long scenic route with multiple intermediate steps and adding up their enthalpy values to determine the overall enthalpy change for a reaction that either is too dangerous, too expensive, or that we don't have the equipment for. Alright, so let's try question 3 together. What I want you to do is press pause. When you're ready, press play, and we'll take it up together. Alright, so the first step is to make sure you balance the equation. If you do not balance the equation, you'll miss out on these coefficients and then nothing works out from that point on. After balancing the equation, we now need to pick which equations we're going to use to assemble them into our target equation. So I'm going to look for H2SO4, which is at the bottom over here, and that'll be equation A. Next, I need to find SO2. Now, the issue we have with SO2 is that there are 2 equations that we could possibly choose from. So which one should I use? In this case, I would recommend we use this one over here. The reason I recommend this one is because with this equation, it involves an S, but our target equation doesn't have any sulfur by itself inside of it. So that might not be the equation I want to use. Now some students will go, well, what about this one? There's an S8 present, and there are no S8s in the target equation. That's true. But there is an S8 in this equation that we were going to use. And so there's a chance that we can use this S8 to cancel out this S8. In any case, if you choose the wrong one, the question just won't work out. That means you chose the wrong one, so go back and pick the other one instead. So trial and error in that sense. But by looking in the equation, trying to find some common elements or compounds that you can use will help you to eliminate which equation you might not want to work with first. So anyway, I'm going to take this equation and label it as equation B. Finally, I need some water. Notice the state of matter is a gas. So I'll pick this equation, H2O gas, and label it as equation C. I am going to ignore oxygen because oxygen gas is an element in its pure natural state, so its enthalpy value is going to be a 0, should not affect the overall equation. Let's start manipulating these equations. I need 2 sulfuric acids, so I'm going to have to multiply equation A by 2. You'll notice that sulfuric acid is a reactant. Well, so is this, so there's no need for me to reverse the equation, so I'm just going to say 2A. With this one over here, I have sulfur dioxide, but I need 2 of them. They're both on the product side, so that's fine. No need to reverse that. So I'm just going to write down 2B. And with equation C, I need 2 waters. Well, multiply equation C by 2. And so my overall net, or my overall game plan anyway, is 2A plus 2B plus 2C. Don't forget to multiply these values into the enthalpy change as well. When I add up the manipulated equations, all of these things will start to cancel out, leaving behind 2 sulfuric acids, oxygen, 2 sulfur dioxides, and 2 waters. And my overall enthalpy is 547.68 kilojoules. However, the answer key says your answer should be in kilojoules per mole of the leftmost reactant. So I want the answer expressed in kilojoules per mole of this guy over here. So in this case, I want it in kilojoules per mole of sulfuric acid. Right now, there are 2 moles of sulfuric acid, so this value, 547.68 kilojoules per 2 moles of sulfuric acid. Well, if I want it per 1 mole of sulfuric acid, I must divide it by 2. In so doing, divide this number by 2, and you get 273.84 kilojoules per 1 mole of H2SO4. And that matches up with the answer we have over here. Alright, so let's give the rest of these a try, and then let's move on to the next topic. Alright, so what I want you to do is manipulate the heats of formation equations in order to solve for the enthalpy value of this reaction. So just press pause. When you're ready, press play, and we'll take it up together. Alright, so the first step is to balance the equation. Oh look, it's already balanced, so that's nice. Now we're going to try and assemble this target equation using the heats of formation equations found at the back here. Hopefully you chose these 3 equations. So let's start manipulating them. Carbon dioxide is on the reactant side. Unfortunately over here it's on the product side, so what I need to do is reverse this equation. In so doing, this negative enthalpy value becomes a positive enthalpy value. Now the carbon monoxide is on the product side, so that's fine, and it also has a coefficient of 1, so there's no need to play around or manipulate this equation any further. The same goes for equation C. The water is on the product side, so that's fine. They have a coefficient of 1, that's fine as well. So only equation A required manipulation. Adding the equations together and canceling out things that appear on both sides, we get the target equation here, and adding up the enthalpy values, we get a total of 41.2 kilojoules. Now the third method is a variation of Hess's law, and it produces the following equation. The enthalpy of the reaction is equal to the sum of all the heats of formation for the products minus the sum of all the heats of formation for the reactants. So that's what this epsilon symbol means. It means summation. So what we're going to do is we're going to see how much does it cost to form compound C, multiplied by how many we want to make, added to how much does it cost to form compound D, multiplied by how many of those we want to create, and then add them all up. So summation, or sum it all up. Then we do the same thing for the reactants. How much does it cost to form A, multiplied by how many A's we want to produce? How much does it cost to form B, multiplied by how many of those we want to produce? Then add those up. We then subtract the total cost of the reactants from the total cost of the products in order to give us the overall net enthalpy change for this reaction. Again, please keep in mind that pure elements in their most stable state are used as a reference point. They are a baseline that we use. Since we can't actually measure enthalpy itself, we had to start somewhere. So by convention, we said that elements in their pure natural state have an enthalpy value of 0. And we use that value as a starting point or a baseline for all other heats of formation values. So here are the equations we're going to use. Notice how I left out the hydrogen because it's an element in its pure natural state, so I can ignore that. Carbon dioxide, equation A. Carbon monoxide, equation B. Water, gas, equation C. So products minus reactants. Carbon monoxide, to form carbon monoxide, releases 110.94 kilojoules. So that's the 110.94 kilojoules. Since they're all a coefficient of 1, we just multiply them all by 1. It's not shown. Then how much does it cost for H2O? For water formation, it's going to release 242.76 kilojoules. So I'm going to punch that in. Add these two together, and that is the total heats of formation value for the products. Do the same thing for the reactants now. Heat of formation for CO2 is 394.9 kilojoules. There's only one of them. And then hydrogen gas, of course, is a 0, so I don't have to worry about that one. Then take this number, add it all up, subtract these two numbers added up, and we get 41.2. So whether we use the equation manipulation method or the summation method with the heats of formation, we still get the same answer. Just make sure that when you're using this method, you can only use heats of formation equations. So those that are found on this chart. So these are called heats of formation because you're forming these compounds on the right-hand side. However, with the equation manipulation method, you don't have to use these heats of formation equations necessarily. You just need some sort of equation to help you build up the target equation. So this method is a little more robust. So if I were to look at this specific example, I can use the Hess's Law equation manipulation method to solve for it, but I would not be allowed to use the summation notation method because it requires heats of formation equations. And these are not equation formation equations. Notice how on this side we've got 2 reactants and 2 products. Same thing over here, 2 products, 2 reactants. But when you look at these heats of formation equations over here, they always have only one product on the right-hand side because it's a formation equation. How much does it cost to form just this one substance? While these equations have you forming multiple substances. Alright, so be careful. This equation can only be used for heats of formation equations. You'll know it's a correct equation when there's just one product on the other side. Meanwhile, the equation manipulation method is a little more forgiving because you can use a variety of different equations and not just heats of formation. Now there is one last topic I want to discuss before I let you go, and that is the molar enthalpy of combustion. So delta HC, or delta H naught C, so remember the naught symbol just means it's under standard conditions, while this one is not standardized conditions. Standard conditions are under 25 degrees Celsius and 100 kilopascals. Well, it describes the change in energy during a combustion reaction. So that's what the subscript C means. It just means combustion. Don't worry about these subscripts. Typically, you'll see like R or RXN or vape or fuse. It's just there to be specific about what kind of energy change are we looking at. So C just stands for combustion. So in this reaction over here, we have butane reacting with oxygen gas in a combustion reaction. When it burns, it releases carbon dioxide and water, but you have to balance the equation with a 2, 13, 8, and 10 ratio. When you see this value over here, it's a negative. So negative enthalpy means it's exothermic. It's giving up energy, 5755.2 kilojoules. You notice it says kilojoules. It doesn't say kilojoules per mole. All right. So as written, you need to burn 2 moles of butane, 13 moles of oxygen, in order to produce 8 moles of CO2, 10 moles of water, and also negative 5755.2 kilojoules. However, if you want to write in kilojoules per mole, you have to specify which one. Typically, what's more important, the fuel or the oxygen, carbon dioxide, or water? We're usually more interested in the fuel value itself. So when they ask you to express the answer in kilojoules per mole, usually we like to express in kilojoules per mole of the fuel that we're burning. So right now, 2 moles of butane are required to release this much energy. If I have it in kilojoules per mole, I have to divide everything by 2 in order to get it per 1 mole of this. Obviously, we'll have fractions at this point, but that's not a big deal. Alright, so enthalpy values found in data tables are typically expressed in kilojoules per mole of the substance being combusted. Thus, when using these values, the coefficient in the equation should be rewritten to convey this. Fractions may be necessary to get to that point. Alright, let's take a look at this question. Under standard conditions, how much energy is released when 3.8 grams of methanol is combusted? So what we have here is 2 moles of methanol, when it combusts, will release negative 1452.2 kilojoules of energy. But are we burning 2 moles of ethanol? No, we're burning 3.8 grams of methanol. So that's like saying I'm driving at a rate of 50 kilometers per hour. Does that mean I drove 50 kilometers? No, it depends on how long I've been driving at this speed. Similarly, this reaction releases 1452.2 kilojoules of energy for every 2 moles of methanol being burned. But I'm not burning 2 moles of methanol, I'm burning 3.8 grams of it. So what I need to do first is convert the 3.8 grams into moles so that I can find out how much energy was actually released. Now it's kind of clumsy to say negative 1452.2 kilojoules per 2 moles of methanol. It's better to have it per 1 mole of methanol. So since there's a 2 coefficient over here, I'm going to divide the whole equation by 2, and now it's kilojoules per 1 mole of methanol. So once I divide this enthalpy value by 2, I get negative 726.1 kilojoules per 1 mole of methanol. From there, I'm going to determine how many moles of methanol were being combusted. So mole is equal to mass divided by the molar mass. Mass is 3.8 grams. Molar mass is 32.05 grams per mole. I can find this from the periodic table, which gives me 0.119 moles of methanol being burned. Since I know each mole releases this much energy, then 0.119 moles, well, I can multiply them and find out the total value, which is negative 86.4 kilojoules of energy was actually released when I burned 3.8 grams of methanol.